Okay, welcome back. As continuing from section 5, we're doing sorting a positional list. We introduced the insertion sort algorithm in the context of array-based sequencing. In this section, we develop an implementation that operates on a positional relying on the same level, on the same high level algorithm in which each element is placed relative to the growing collection of previous sorted elements. We maintain a variable name marker that represents the rightmost position of the current sorted position of a list during each pass. We consider the position just past the marker as the pivot and consider where the pivot element relative to the set position. There is another variable named walk to move leftward from the marker as long as there remains a preceding element, the value lecture and the pivots. Typical configuration of this variable list diagram is on figure 15. The overview of one steps of our insertion sorts, including the shaded element, those up to including the marker have already been sorted. In this step, the pivot element should be relocated immediately before the working position. So we have a code of code which have a code method insert sort, and then it's check the length if it's greater than 1, otherwise sort it, then set to the first one, or one is not on assign the pivot in the list after the maker next item, assign the value. The value is greater than marker dot element, means the pivot is already sorted. The pivot, and then must allocate, and then reinsert the value. The case study, maintaining access frequencies. The positional list ADT is useful in a number of settings. For example, a program that is simulate a game of cards could model each person is set as a positional list. And exercise P7 of 47, since people keep cards of the same suits together, inserting and removing the cards from the test sense could be implemented using the method of the positional list editing. With the position being determined by a natural order of the suite, likewise, a simple text editor embeds the position of the embeds the notion of the positional insertion and deletion. Since such editors typically perform all updates related to a cursor, which represent the current position of characters of the text being edited. This section will consider maintaining a collection of elements while keeping track of number of times each element is accessed. Keeping such access count allow us to know which element among the most popular. Example of such scenarios include a web browser that keep track as a user's access URL, or music collection. Or music collection that maintain a list of the most frequently played songs for a user. The model the new favorite is ADT that supports len and the empty method, as well as the following. The accessor or access element E, access the element E, incrementing its element counts and adding it to the favorites list if it's not already present. Remove the element E from the default if it's present. To K, return an annotation of K most access elements. Using the sorted list, Our first approach of managing a list of favorites is to store elements in a linked list, keeping them in an increasing order to access more counts. We access or remove an element by searching the list from the most frequently accessed to the least frequently. Reporting the top key access element is easy, as they are the first key entries of the list. To maintain invariant, that elements are stored in an increasing order of access count. We must consider how a single access operation may affect whether the access element count increases by one, or so it become larger than the one or more of its preceding neighbors in the list, thereby violating the invariant. Fortunately, we can re-establish the sorted invariant using the technique similar to the single pass of the insertion sort algorithm introduced in the previous section. You can perform a backward traversal of the list, starting at the position of the element where whose access count has increased, until you locate a valid position, after which the element can be relocated. Using the composition pairing, we wish to implement a favorite list by making use of positional list posterity. Element of the positional list, simple element of the favorite list, we will be challenged to maintain an access count and to keep the proper count the associated element. As the contents of it are reordered, we use a generally object-oriented design pattern, the composition pattern, in which we define a single object as composed of two or more objects of the other object. Specifically, we define a non-public nested class item that stores the element and its access counts as a single instance. We maintain our favorite list as a positional list of the item instance, so that the access count for users element is embedded alongside our representation. An item is now exposed to a user of the favorite. So we have a class favorite list. This we list the element from the most frequency access to list, and then we create a nested class, which is item, with the same knowledge of the value and count. Define the method, set it to a user's value, and then set the count to 0. I will do a method to find the position search of element E and return its position. We have done a worker where we're searching the position, working around it. And then we do the move up method, move item to the position P area in the list based on access account. We initialize the initialize method, which creates an empty list of favorites, will be a list of intents. Then we check the length or the number of entries, and then we check if it's empty. And then we do a method access an element E by increasing its access count. Try to locate the existing element. And then if the new, place it at the end. Always increment the count, increment by 1, and then we're moving forward. Remove element from the list of the favorites. Try to locate the existing element, delete if it's found. Generate the most frequency access element, or generate a sequence of a top element in terms of access account. Using the list, we can move to find heuristic. The previous information of the favorite list performs the access element of E method in the term proportional to the index of E in the favorite list. In essence, if E is the k most popular element in the favorite list. Then accessing its k, it takes the peak of k time in many real life accessing sequence, e.g. web pages visited by a user. Once an element is accessed, it's more likely to be accessed again in the near future. Such arrows are said to be the locality of reference. A heuristic or rule of thumb that attempts to take advantage of the locality of reference that is present in an access sequence is to move to the front heuristic. To apply the heuristic, each time we access an element, we move it all the way to the front the list. Our hope, of course, is that this element will be accessed again in the near future. Consider, for example, a scenario in which we have n element and the following scenarios is the following series of n squared accesses. Element 1 is accessed n times, element 2 is accessed times, etc. If we store the elements sorted by access accounts or count, inserting each element, the first time it is accessed, then we go with each access to element 1 and in constant time, and each element 2 runs in peak of 2, which is constant time, and each access to element n runs in the n time, which is linear. That's the total number performing the series of access proportional to n plus 2, n plus 3, n, etc., which is the peak of n cubed. On the other hand, we use the move to front heuristic inserting each element the first time is accessed. And then we subsequently access to element 1, constant time, element 2, constant time. So the running time of the performing all the access in this case is the n squared, which as the move to heuristic implementation as fastest access time for the scenario. Still move to front approach is just heuristic. Access sequence where using the move to front approach is slower than simply keeping the favorite list or that by the access count. The trade-off with the move up to front heuristic, if we no longer maintain the element of the favorite list by the access count, when we ask to find the key most access element, we need to search for them. We will implement the top key method as follows. We group all the entries of our favorite list into another named temp. We scan the temp list k times. In each time scanner, we find the entry with the largest access count, remove this entry from the temp, and report it in the result. This implementation of the method top k takes the peak of k of n, or peak of kn times. That is a constant method tops runs in the peak of n or the linear terms. This occurs, for example, when we want to get the top 10 list. However, if the k is proportional to n, then top runs in peak of n squared times. This occurs, for example, when you want top 25% in this. In the following chapters, we will introduce the data structure which allow us to implement top in the peak of n plus k of log times. We can easily achieve the peak of n log n time if we use the standard sorting algorithm to reorder the temporal list to perform reporting to top k. This approach will be preferred to the original in the cases that k is the peak omega of n. When you record that the peak omega notation introduced in section 3, in section 3 or chapter 3, to give a symptomatic lower bound in the running time of an algorithm. There is a more specialized sorting algorithm for the coming section that can take advantage of the fact that access count are integers in order to achieve the peak of n time for the top for any value of k. Implementing the move to find heuristic in Python, we give an implementation of a list using the move to find heuristic in the fragment 20. The new favorite list TF class inherits most of its functionality from the original favorite list as a base class. By our original design, the access method of the original class relies on a non-plug utility name move up to enact the potentially shifting element forward. The list of its access count had been implemented. Therefore, we implement a move up to find a heuristic by simply overriding the move up method so that each access the element is moved directly to the front of the list if not already there. This action is implemented by means of the positional list. The more complex portion of our favorite list, MTF class is the new definition for the top method. We rely on the first for the approach outlined above, inserting copies of the item in the temporal list, then repeatedly finding, reporting, removing an element that has largest access count of those remaining. Running this program, we define a class favorite is class with a list of other move to front heuristic. We override a move up to provide a move to front semantic method called move up, which move access to front of it. And then we have a top generated token of top k element, and then we're positioning them begin by copying the original list. And then we run a for loop repeatedly to find reports and move the element with the largest count. Link base vs array base sequencing. We close this chapter by reflecting to the relative pros and cons of array base and link base. There's a structure that's been introduced thus far. The dichotomy between these approaches present a common design decision when choosing an element and appropriate implementation of data structure, that there is no one-size-fits-all solution as each offers distinct advantage and disadvantage. The advantage of array-based sequencing. Array provides a constant time access to an element based on an essential index. The ability to access the key elements for any k is constant time in a hallmark advantage of arrays. In contrast, locating the key in a linked list require the peak of k time to traverse the list from the beginning, or possibly the peak of n minus k time traversing back from the double linked list. Operation with equivalently asymptotic bounds typically run constant factor more efficiently with an array-based structure versus a link structure. As an example, we consider the typical enqueue operation for a queue, ignoring the issue of resizing an array. This operation of an array queue class involves an arithmetic calculation of index and increment of an integer and storing a reference to the element in the array. In constant, the process will require the extent of the integer, while this operation completes in a constant time in either order in actual numbers. The actual number of CPU operation will be more in a link region, especially given the initiation of the new nodes. An array-based representation typically are proportionally less memory than a linked structure. This advantage may seem counterintuitive, especially given that the length of a dynamic array may be longer than the length of n elements that it stores. Both array-based link and linked list are referential structure. So the primary memory for storing the actual objects that are elements is the same for either project. What differs in the auxiliary amount of memory that are used by the two structures, where an array-based container of n elements are typical with case may be that a recently resized dynamic array has allocated a memory of to n object references. With the linked list, memory must be devoted not only to store a reference to each contained object, but also explicitly references that link the nodes. So a single linked list of length n already required to n references and n references and nest references for each node. With the double linked list, there are three n references. Advantage of a link-based or linked list sequence. A linked list-based structure provides a with time bound for their operation. This is a contract to the amortized bound associated with the expansion or contraction of a dynamic array. When many individual operations are part of a larger composition, and we are only care that the total number of the composition and amortized bound is then put as with case bound precisely because it gives a guaranteed and on the sum of the time spent on the individual operation. Structure operations are used in a real-time system that is designed to provide more immediate response, e.g., an operating system or server, a traffic system. A long delay caused by a single amortized operation may have an adverse effect. The linked list structure supports content time, insertion and deletion at arbitrary position. The ability to perform a content time insertion and deletion with the positional list class by using position to efficiently describe the location of the operation. It's perhaps the most significant advantage of the linked list. This is a stack contrast to an array-based sequence, ignoring the issue of the resizing an array, inserting or deleting an element from the head for the end of the array-based list can be done in constant time. However, more general insertion and deletion are expected. For example, with the Python array-based list, class a call to insert or pop with the index k uses the peak of n minus k plus 1 time because of the loop to shift all the sequence or subsequent element. An example of application consider the text editor that maintain a document as a sequence of characters. Although users often add character to the end of the element, to the end of the document, it is also possible to use the cursor to insert or delete one or more characters at the arbitrary position in the document. If the character sequence were stored in an array based sequence, such as the Python, some edit operation may require a linear many characters to be shifted, leading to the peak of n, which is linear operation. Performance for each edit operation with a linked representation and arbitrary edit operation insertion or deletion of character at the cursor can be performed in a constant time. This case time, assuming we are given a position that represents the location of the cursor. Checking on the exercise, maybe we can start at looking at the notes. First create a class node, name it node, and then we create a method in it with a self parameter, and then we distribute it as assign to 9 data parameter. Then we have a self dot answer and the data. Then we have self dot next. We know when we have to try this, we have to go to the next one. We assign to 9, so for now is 9. And then we nested the linked list. We define a method here in it. So, so let's give it head. This is the first one. We give it the head as the first one. And then we assign to class node one with the 4. And then we define maybe this way you're gonna change the list. Self, then as a data. Then create a new node. Thank you. Thank you, Sammy. Define a new node, then you assign to the node that we created before. Say current. Now define a current. We assign to self dot head, because current is the first one that must be in the head. While current dot next is not, this exclamation means is not 9. And then we set current, assign to current dot the next one. And then assign current dot next, assign to the new node. And we need to define the length to check how many here. Define the length, the method. And just use current. And set that head. Then the method. Now we keep it to 0. while current dot next is not equal to none. So we increase what that is so we increase while current dot 29 increased by 1. So let's get increased by 1 is the current. Assign current to the next. Then we return the total. Then we take the fund display. We're going to display. Assign to set. There's the element. For now, let's assign them to empty. So correct node. Assign to set, calling the one in the parameter head. And then 1 current input node. We need to send to the next one. Yeah, next one. The element and append method. When the method is current to data, provide data, then print. So when the owner is gonna work, then let's list. Let's see if calling my list to display. Okay, let's see if it's gonna work. Okay, so let me check on it. I think there's an error while current nodes dot next. It's not equal to 9. And then say element, and then say current, no, doesn't current dot next. I think should be fine, hopefully. Okay, we create a class, and then we have a method, init initialize, and then we initialize the data to 0 to none, and then set the data to data, and then the next to none. And then we have in nested list. We have a class code. Let's say link. I'm supposed to say list. That's fine. So class, and then need to append any data we got, and then you check the length, and then you must display here. So if we got it wrong, we should for the first time before we put anything, we must put an empty list. You can see that it got empty here because it's empty. So let's say if we add 1, let's say if we add my list, we're calling the that append, we're calling the append list. Let's give it the 1 list. We'll append again. It should give us these 3 lists. If I'm not taking my list dot okay. I can see now it's 1, 2, 3 is that we have. Okay, that means it's a node. It's in a node from here. This is the first node, and this is the node. And then to the linked list, this is the node which was 1. Then to the next one, which was 2. And then went to the next one, which was 3. It's just calling it to display them. Unlike when you're running an array where you can access them with an index. An array you can access it with an index like, okay, this is 0, index 0, index 1, index 3. On a list, you arrest them with a connection of next or previous or head. We're using the node to get them. It was with this example, it made a little much more clear than before. We have 1 minute left, or less than a minute. I think the exercise I'll do it later. But this one is giving an example, giving an implement for this, or just push with them on our GitHub. Given looking for finding the element to last node of the next heap. First one I not much. So, but guys, this was a long topic. Was it how was it? Was it clear?